welcome to our latest webinar as part of the Sporty's webinar series on airplane engine operations. My name is Brett Kobe. I'm with Sporty's and I'll be your facilitator this afternoon. A little bit about our presenter. Ryan Cook is a commercial pilot and CFII. He's Director of Product Development for Pilot Workshops. Those that have known the company and brand have seen many of his works over the years. Specializes in IFR training, avionics training, and flight simulation. Has produced content in the form of manuals and courses for pilot workshops. And most notably, his most recent production along the similar lines of this topic here today in the webinar is an airplane engine operations course. And a lot of the content here in this webinar originates from this product, and highly recommend anyone who is looking for more information and wants to know even more and wants to thirst that quench for how to really get the most out of their engine to check out this course. It's video-based, so you'll be able to see the effects throughout all phases of flight, really from startup to shutdown, using a graphic engine monitor, best practices to increase the longevity of your engine, but also things like how to get the best fuel consumption. And Ryan will touch on a lot of those topics today, but this course is a great way to, again, follow up on that and learn a lot more about that information. So with that, Ryan, welcome to the webinar, and I'll turn it over to you.
Thanks, Brett. Thanks, everybody, for coming. So let's dive into airplane engine operations. This is a really big topic, obviously, and the thing that makes operating an engine, I think, tricky or confusing is that there's just a lot of conflicting information out there. There's a lot of information out there total, and a lot of it disagrees with each other. You get everything from experts who can give you lots of great detail, lots of technical solutions. A lot of that is excellent. All the way to the other end of the spectrum, where you have dozens of YouTube videos on every topic from CFIs and pilots, and some of those are good and some of those are not at all. But the bottom line is it's kind of all over the place. And then there's a lot of tribal knowledge that gets passed down. And this is one area where you can't necessarily fall back on the just follow what the POH says. And that's because a lot of these POHs are 50 plus years old in these light GA airplanes. And so they're not informed at all by the 50 years since they were published, right? With all the better understanding of techniques, better engine monitoring. And they certainly don't assume that you have an engine monitor in the panel. So it's not as simple as follow the POH here. So what the video course that Brett just mentioned does, and what we're going to do in this webinar, is try to distill this down into user-friendly, practical techniques, give you enough of the concepts that you can apply them to whatever your mission happens to be and whatever you're flying. I should disclaim here, I'm not an A&P. You wouldn't want me looking under the cowl of your airplane or doing anything to it for sure. But I come at this from a user and a CFI perspective. The focus of this webinar is going to be mixture management. There's a lot more to operating an engine than just mixture management, but we've got an hour, and mixture management is a topic that I think causes probably the most confusion, or there's the most variety of techniques, or in some cases, fear to even touch the red knob. So that's what we're going to focus on here. The discussion is also going to be limited mostly to normally aspirated Lycoming and Continental engines. If you fly something that's turbocharged, you'll still be able to get things from this webinar for sure, but the specific examples won't apply exactly to you. And if you fly something, without a mixture knob, something with a FADEC, or if you fly Rotax or something, good for you. Stick around though. Hopefully you'll still get something out of this. Primarily, we're talking about normally aspirated Lycoming Continental engines. The organization of the webinar, we're going to tackle 3 topics. First is to try to build up a conceptual understanding of what the mixture control does and how that relates to the different things you might have as goals and things you might be trying to avoid. And then we're going to apply that knowledge to 2 specific situations. The first is cruise for simplicity, where we're going to take an old school technique and see how it stacks up in the modern world of engine monitoring, and how we can adapt it to modern techniques. And then the second example is how not to waste too much fuel climbing. This is a phase of flight where many pilots are especially reluctant to touch the red knob, but you can, in most cases, do more with the mixture than you might think. This is the basic question that everybody has, is just how should I operate my engine? And if there's one takeaway from this webinar, it should be that there is no single right way to operate an engine. There are probably some wrong ways, but there's not necessarily a single correct answer for this. And you might think, sure, that's because different engines, different airplanes, but actually, at least within this category of normally aspirated Lycoming Continental engines, there's a lot more similar than there is different between them. So really what I'm talking about when I say there's not one correct way to operate an engine has much more to do with your goals, your values as a pilot, and just day-to-day missions. What are you trying to get out of the engine in this flight? And the technique that you choose is going to be catered to that. So broadly speaking, what are some of those goals? What are some of those things that you're trying to avoid? On the goals side, these are all on a spectrum with trade-offs relative to each other. These are all a compromise. You can't really have all these at once. But you might be going for efficiency or economy that'll be at the expense of speed. For example, if you're trying to get somewhere and you want to go there, you want to get there fast, of course, you're going to burn more fuel doing it. A third goal that sometimes gets overlooked here is simplicity. There are some techniques that you might adopt that are ideal on a test stand, but have enough pilot workload involved that they're not ideal when you're at the final approach fix of an ILS or flying VFR into Bravo airspace. We need to acknowledge that we're also flying airplanes here, and sometimes simple techniques there's really something to be said for simplicity. The other side, then, the things that you're trying to avoid, obviously engine abuse. You want to maximize the longevity of your engine. You don't want to do anything that will damage it in the short term either. You don't want to waste fuel for no reason. There are certainly some situations where you have to burn more fuel than would be, maybe chemically ideal. But in general, we're not trying to just waste fuel. And then the flip side of simplicity is techniques that are demanding and require an increased pilot workload are things that we want to avoid to an extent that depends on what situation we're in. So all these things can vary from day to day, what you want to get out of the way you're managing the engine and flight to flight. So what we're going to do is identify some of these landmarks using this chart. And what you're looking at here is mixture versus horsepower, mixture versus power output. And we're going to expand this to include more curves, more parameters in a moment. But let's start here. So the horizontal axis on this chart is the mixture setting or the fuel flow. At the right side is the full rich mixture. Moving to the left, you get leaner. Eventually, you get all the way to the left to an idle cutoff position. The green curve then is how horsepower relates to that. If you start all the way over at full rich, we're making slightly less than the maximum power we could be. And, this sounds like a lose-lose, right? We're producing less power and burning more fuel, but again, sometimes that's necessary. We'll come to that in a moment. Move to the left on this curve, pull the mixture knob out further. Eventually, we get to a point where horsepower is maximized. So this is our peak power point. And you'll note the vertical green dashed line here that marks this landmark. And that'll be a reference that stays on this chart as we go forward and add more to the chart. Peak power is something that's easy to find if you have a fixed pitch propeller. You just lean in order to maximize the RPM. It's a little trickier if you have a constant speed propeller, but there's various techniques to do that. Continue moving to the lean side of the chart, and we get to a point that we'll call best economy. This is the least fuel for a given horsepower. So this is where we're maximizing for economy. And we're just conceptualizing this at the moment. We'll quantify things in a moment. If we were to continue leaning beyond this point, there comes a practical limit on how lean we can actually get. And that's when roughness occurs. So eventually, if we keep leaning, we're going to start to feel and hear engine roughness. That's the practical limit on how lean we can go. Why is that happening? Why do we run into roughness? It's not that any cylinders are misfiring. It's not that cylinders are too lean for proper combustion. Actually, the reason has to do with having multiple cylinders. So right now, the diamond on the chart is depicting a single cylinder. In reality, this Comanche that's in the picture and that we'll be using for examples here has 6 cylinders. And those cylinders get different amounts of fuel. And so they fall at slightly different points on this curve. So this is what that looks like when they're on the rich side of the curve. We've got an R marking the richest cylinder and L marking the leanest cylinder. The difference laterally, horizontally from each other is the different fuel flow that those cylinders are getting. The other four fall somewhere in between. And you can see that they're basically producing the same amount of power. The curve there, the horsepower curve, is pretty flat, so there's not a whole lot of difference in the power that they're putting out now. And so it's going to feel like it's running pretty smooth. If you continue, well, this actually shows that on one more slide here. So the vertical lines are how far apart they are in fuel flow. The horizontal lines mark the fact that it's a pretty small power difference that results from that. But if you move over to the lean side of the curve, same distance between the cylinders, same distance between the vertical lines. So the fuel distribution between the two is just as different as it was on the rich side. But now that corresponds to a much larger power difference. And that's what we feel as roughness when you lean far enough. All you're feeling is different power output on different power strokes, different power pulses from each cylinder. Each cylinder here is fine independently, but we're not going to hang out here because of the roughness. And that becomes an obvious feeling. So where that limit is, how lean you can actually get, depends on how tight the fuel distribution is between cylinders. So a typical carbureted engine that doesn't have great fuel distribution, there's going to be a wider spread between the leanest and the richest cylinders. And you're not going to be able to get it quite as lean as you would if you had, say, a fuel injected engine that maybe has tuned injectors like GAM ejectors, keeps the fuel distribution really tight. Each cylinder is getting much closer to the same amount of fuel as the others. And so as a result, you can go much deeper onto the lean side of the curve here before the power difference becomes noticeable as roughness. And so this is primarily why things like GAM ejectors are desirable. They let you achieve a leaner mixture. So far, just looking at power versus mixture, we've identified 2 points that maximize for something, whether it's power or economy. So it seemed logical that we could pick one of those, depending on what our goal is, or pick some compromise in between and run with it. But of course, that's not the whole story, because we still have things that we want to avoid, like potential abuse to the engine. So we've expanded this chart now. We still have the horsepower section at the bottom, but now at the top, we have a blue curve that's labeled CHT/ICP. And this represents how potentially abusive the mixture setting could be. CHT, of course, is cylinder head temperature. This is something that is on the engine monitor, and it's a good indication of stress. High CHTs can be damaging to the engine or can limit its longevity. We'll get to what practical realistic limits should be in a moment, and they're not the same as the manufacturer limits in most cases. But CHT is one element of the sort of abusiveness equation. The other side of this is ICP, or intracylinder pressure. This is not something that we measure, that we can see on the engine monitor, for example, but it turns out that CHT is a really close proxy for ICP. These curves look pretty much the same. So what we've done to simplify it for the pilot perspective here is sort of merged and abstracted them into a potential abusiveness curve that you see here. So the points that are useful on this curve, we'll start with full rich. Full rich, we have extra fuel cooling and the different effective timing, and ultimately we end up with lower CHT and lower ICP at full rich. So even though we're burning more fuel and producing less power, there are some instances, like when we're making close to full power, we'll get to that in a moment, where we just have to operate here because of how it reduces CHT and ICP. Moving to the left, lean mixture sum, we have a point here where we're at the peak of the curve, the CHT-ICP curve, which we'll call peak abusiveness or peak potential abusiveness. And this is just slightly leaner, but pretty close to where we find peak power. So you can see that these two, the pros and cons are at odds with each other here. We get peak power right next to where we get peak abusiveness. But how do you know if it actually is an abusive mixture setting? How do you know if this is a problem? Well, that's where this concept of the red box comes in. This is something that you may be familiar with on some level. But the red box is the area here where CHT and ICP is potentially high enough for long-term damage or wear, or that would reduce longevity, or in extreme cases, if you get far into this box, you could reduce the detonation margin enough to actually encounter detonation. So the way the chart is, or what the chart is depicting right now, is 60% power. You can see the power meter at the bottom of the chart. And at this point, there's no intersection between our abusiveness curve and the red box. Just about touches it, but not quite. And so generally speaking, if you're making 60% power or less, you can put the mixture anywhere and not worry about hurting anything. But as we produce more power, now we're at 65%, typical cruise setting. Now there is some overlap. See that blue curve shifts upward because we're producing more power, we're producing hotter temperatures and higher pressures. The curve shifts upward, and now there's some intersection with the red box. And so conceptually here, again, we need to either be rich enough to avoid it or lean enough to avoid it. Push that up to 75%, which is a typical sort of go fast cruise power setting. People often use this as a practical maximum for cruise, and it's not a limitation. You can certainly cruise at a higher power setting than this, but this is one reason why it's a good practical maximum, is that you'd have to be quite rich to be clear of the red box here, or pretty far lean to be clear of the red box. So there's a whole range of mixture settings in the middle that are potentially not going to be great for the engine. So while it seems logical to pair some go fast goals here, the 75% cruise power with the best power mixture, you can see that the problem here is you're potentially doing some damage. Shift that curve up even further. Now we're at basically 100% power, and almost the entire curve overlaps with the red box. And so in this case, we need to essentially be at a full rich mixture. So again, we've kind of just been all conceptual at this point. How do we actually quantify this? The way that we typically do it is by using EGT, exhaust gas temperature, as a reference. And I want to lead on EGT with the fact that EGT, the absolute number doesn't matter. EGT is not something that's harmful for the engine. High EGTs are not a problem. It's strictly a reference. So EGTs on this engine monitor are represented by the blue bar graphs. There are also the numbers, the highest of the two numbers in the groups above that. Most of them are in the 1400s range. Sounds extremely hot because the probe is just directly in the exhaust gases, whereas the CHT is actually measuring the temperature of the metal, which takes a little while to change. And that's also why EGT is a useful reference for this, because it does change quickly, whereas CHT lags further behind. But EGT, it's somewhat a measure of energy wasted out the exhaust, and that says something about the fuel-air ratio, and that's why we can use it to quantify where we are on the mixture curve and get a sense for what the implications for that would be. So let's do that. This is what the EGT curve looks like superimposed on the CHT ICP curve. The EGT curve is in orange here. Ignore the absolute value here. They're just plotting it on there for comparison. It's not significant that this enters the red box, because that's not what the red box is about. But the way the EGT curve works, it starts at full rich at a pretty low value. As you lean the mixture, it increases. Eventually, it reaches a peak, and if you continue to lean, it drops off. The temperature drops off on the other side. And we can quantify our mixture position by using EGT as a reference in terms of the degrees rich or lean of where EGT peaks. So we'll add that to the horizontal axis here. We've got peak EGT in the middle. And then for each vertical line, each vertical dashed line there represents a 50-degree interval of EGT. So if we're saying something is 50 degrees rich of peak, it's where the temperature, the EGT, is 50 degrees cooler than it is at peak on the rich side. If we're saying it's 50 degrees lean of peak, then we leaned past the peak position to where the EGT dropped off by 50 degrees. So now we can plot some of those landmarks on this curve with reference to EGT. So peak power occurs at about 80 degrees rich of peak. Peak abusiveness, pretty close to there, is at about 50 degrees rich of peak. 50 degrees rich of peak might ring a bell because a lot of POHs suggest running the engine in cruise at 50 degrees rich of peak. And it turns out that in many cases is the worst place that you could run the engine, at least in terms of the potential to be running a high CHT or an ICP. If you continue leaning, you get to a point that our range really of best economy that falls somewhere between 80 degrees lean of peak and 20 degrees lean of peak, depending mostly on total power output. If you're at higher power settings, it's closer to the 20 degrees. At lower power settings, it's closer to the 80 degrees lean of peak. The usual technique, often involving use of something like lean assist or lean find on an engine monitor to find these points, is to lean watching the EGT until it peaks, and then either enrich until it goes down by the degrees rich of peak that you want to be, or continue to lean until it drops the degrees lean of peak that you want to be. That technique is not necessarily the best approach to do routinely, because you end up spending a lot of time in the red box. You end up spending a lot of time heads down, slowly leaning and watching the numbers tick away when, maybe your attention would be better spent on some other flying task. And it's often not necessary to do it that way. We'll give some specific examples, but that's traditionally the way it's done. Watch the peak and then enrich or lean to the desired number of degrees rich or lean to peak. We could say something here about where the red box exists in terms of degrees rich or lean to peak at different power settings too. So here we're looking at 75% power. Again, this is the kind of high cruise power setting. And we need to be about 175 degrees rich of peak. Or if the engine can do it, we could also go 50 degrees lean of peak in order to avoid the red box here. Drop it to 65% power. Now our potential no-go range is between peak EGT and 90 degrees rich of peak. Anything richer or leaner than that range should be clear of any problematic CHT or ICP combinations. And again, drop it to 60% and you're in the clear. You should be able to set the mixture anywhere you want. So again, we've been talking about a single cylinder as an example here, but the reality is that we have multiple cylinders. So let's bring back our leanest and richest cylinders and consider which one we care about. So on the rich side of peak EGT, we care about the leanest cylinder, and that's because it's the one that's going to be closest to the red box. So in this 75% cruise, rich of peak scenario, it's not just that we have to be 175 degrees rich of peak, it's that our leanest cylinder has to be there, and that puts us even richer on average than that. So it's really not a very economical way to operate. Unless you can get to the lean of peak side, that it is a very economical way to operate. But we have to get even leaner than you might think, because that 50 degrees lean of peak to clear the red box on that side has to be the richest cylinder, so that all the others are leaner and further away from have lower CHTs, lower ICP. It should point out though that the red box is not a hard line. It's not an absolute concept here. It's fuzzy. These aren't hard and fast rules. You might be fine with being a little ways into it, whereas you might not be fine being deep in the red box. This is a case for real-time data mattering just as much as these concepts. And so as you're doing this, the thing really to look at is CHT. In most cases, CHT is a pretty good proxy. And if you can keep CHTs at reasonable levels, more on what reasonable levels mean later, then you can have a little more confidence of dipping your toe into the red box a little bit more. Whereas if CHT is high, you may err even farther away from where the red box is in principle. Okay, so that's the kind of conceptual baseline here. We're going to start looking at some specific examples, but first I'm going to throw up a poll. And assume for this that you fly something normally aspirated Lycoming or Continental engine that has a mixture control. And the question is, how do you typically lean for cruise? So we've got, really even split here, basically 25% that use lean find and lean assist, 24% that lean to a known fuel flow, 20% that do it by feel and sound despite having an engine monitor, 24% that do it by feel and sound and don't have an engine monitor, and 7% do something else. So what we're going to talk about here is kind of by that by feel and sound technique and how we can merge that with modern tech and where it actually puts us, what it actually accomplishes. And so this is a back to basics, old school technique. Here's what it is. This is probably something that you may have been taught from the very beginning for how to lean for cruise, if you were taught to lean at all. And so your simple cruise leaning checklist goes like this. It's first of all, lean until you experience some roughness. And then step 2 is enrich just enough to make the roughness go away. So really we're leaning, getting the engine as lean as it can go while still running smoothly. And this may sound like it's a basic beginner technique, but actually it's a good technique. It's at least a really good starting point, depending on what you're trying to achieve. And it works well at reasonable power settings, works in any aircraft, but the exact results, where it puts you on the curve that we just talked about, is going to vary depending on what you're flying. So this example is from that Piper Comanche, the one that we use as an example aircraft in the course. And the leanest practical mixture, the one that we get by using this technique in that plane, lands us with the richest cylinder right at about peak EGT. The leanest cylinder is about 50 degrees lean to peak, and the rest falls somewhere in between. You might be surprised, this being an old school technique, that the end result is a lean to peak. It was this lean to peak operation. But if you think about what that roughness actually is, it makes sense. The roughness is the difference in horsepower across cylinders, and that happens, it's brought out more by the steep lean side of the horsepower curve here. And so in just about any engine, if you truly lean to the onset of roughness and then enrich just enough to get it running smoothly again, at the very least, the leanest cylinder is almost certainly going to be lean at peak. And you've probably got other problems if it's not. The richest cylinder, in this case, is right at peak EGT. The way that you might figure out where things land here is to lean and watch every cylinder peak in turn and find out which is your leanest, which is your richest, and then be able to figure that out with respect to peak EGT. You don't have to do that every time though. Once you know where it lands, you know this technique is going to put you in the same ballpark each time. So what does this achieve? Well, it basically achieves the best economy that we're going to get in this plane. So this is that best economy range, which is typically between 20 and 80 degrees lean to peak. And for the most part, the cylinders here are all in that range, except the richest one. But the reality is we can't get any leaner than this. So really nice intuitive rule of thumb in this plane, and in many, is the leanest that you can get is the most economical that you can get. Nice simple rule. When is this a valid technique? Again, in this plane, with respect to the red box, 65% power is a nice practical limit, or at least a starting point. The richest cylinder at peak EGT here, 65% power, just about touching the red box. If we were to go up to 75% power, same technique, still is going to land us in about the same place. But now that richer cylinder, the one at peak EGT, is in the red box. And it's worth noting here, I think, that lean to peak has a reputation. Just start a conversation in any FVO about lean to peak and sit back and watch. But lean to peak has a reputation for being potentially damaging, and usually the misconception is that leaner is hotter, and therefore you get too lean, you risk doing damage to the engine. But this makes it clear that it's not the lean cylinder that's the problem. It's not being too lean. It's not the problem is not being lean enough. It's the richest cylinders that you might have a problem with. And so there's a variation on this technique that's actually problematic in this light, which is you do the same thing. You lean for roughness, you enrich for smoothness, and then just for a bit of extra fuel, a bit extra cooling is so it goes. The saying goes, right, is you enrich by just a few more twists, and you can see why you don't want to enrich a few more twists. You want to, if you do this, you want to lean aggressively, get it as lean as it can go. Now imagine we're in something with better fuel distribution. So this is a Bonanza with an IO550 with tuned fuel injection. And in this case, the fuel distribution between each cylinder is tighter. And so we can get further on the lean side before we encounter any roughness. Even leaner here than technically where that best economy range is. And so, you might think that you want to then tweak it with reference to peak EGT again to get yourself square in the middle of this best economy range. But actually, a better way to do this is not to bother with EGT, but to use the data that you actually care about. If you care about economy, take a look at what sort of efficiency you're getting. If you have this data displayed on your engine monitor, if you have it connected to a GPS like we do in this case, you can read out directly what your miles per gallon is. And if you're trying to maximize miles per gallon for a given percent horsepower, this is where you want to do it. This is what you're actually trying to lean for. You might also be leaning for, say, a certain amount of reserve fuel or time at your destination, or you might lean for endurance or fuel required. All slightly different ways of tuning for the same thing. But in general, it's better to get the mixture in the ballpark and then adjust it in terms of what you actually are trying to achieve, rather than using an arbitrary EGT reference. And so the other thing to do here, of course, is to always verify with CHTs. CHTs are still in the normal range. Go ahead and lean for what you're actually looking for. This is related to a technique that you might hear usually with respect to lean to peak operations called the big mixture pull. The idea is to get as lean as practical in one smooth pull of the mixture. So pull the mixture back, somewhat quickly, until you either run into that roughness or you feel the power output drop off, and so you're on that side of the curve, and then just use real-time data to tweak it from there. This was one set of values that emphasized efficiency and economy, but you might resonate more with this quote: "We don't fly airplanes to go slow." And then there's a whole other set of considerations. We have some examples of what you might do if this is your goal in the course. But for the webinar, we're going to move along to a climb example. And we'll lead that off with another poll question. So the question here is, when do you lean in the climb? Do you lean only above a certain altitude? Only below a certain percent power? Do you lean continually throughout the climb, or do you never lean in the climb? Okay, so we've got our winner here is continually throughout the climb, which is basically what we're going to talk about next. So that's great. Only above a certain altitude is in second place, and then actually never is in third place, and last is only below a certain percent power. All right, so our next example is how not to waste too much fuel climbing. And, full rich at sea level, full power is essential. It's just what you have to do to keep the engine cool. But it is okay to lean really anytime above that. But when and how? First of all, it should be said that the most important thing here is engine cooling. This is the critical thing. We're operating at high power, low airspeed, not as much cooling airflow. And so maintaining the temperatures at a reasonable level is really your top priority in most cases. This is what things look like at full power at sea level. And you can see again why we definitely need to be very rich to avoid doing any harm here. And the mixture is set up such that it's rich enough, at least it should be set up such that it's rich enough, provides enough fuel flow for cooling at 100% power and at a sea level density altitude. What you do from there as you climb There's various techniques. POH guidance is kind of all over the place on this. It tends to be on the conservative side, but not always. The Comanche in the example we've been using, the POH for that says that above 5,000 feet density altitude, mixture should be leaned for takeoff and presumably also for climb only until any engine roughness is eliminated. This is pretty conservative. At 5,000 feet and a full rich mixture, you may not even experience any roughness, but you're certainly not getting as much power as you could. You're certainly using a lot more fuel than you have to there. 172S POH is much more aggressive with its leaning technique. It says above 3,000 feet, you should lean for maximum RPM. At 3,000 feet density altitude, we're still making more than 80% power there. So 80% power combined with maximum RPM, if you think back to the red box slides that you saw a moment ago, that's going to be squarely in the red box. So that actually maybe is a bit on the aggressive side. And then this normally aspirated PA32 just says maximum continuous power and full rich mixtures. Doesn't even say anything about leaning in the climb. That's just a representative sample of what POHs tend to say. It's kind of all over the place. The reality here is that if full rich is adequate for enough cooling at sea level and 100% power, then any density altitude above that technically is richer than necessary, right? As we climb, the fuel air ratio gets richer naturally, the power output decreases, and so we get an even greater cooling margin with the fuel, and the red box is shrinking as we climb. And so in principle, what we could do is lean to maintain the same fuel air ratio as we had at takeoff, or the same cooling margin essentially that we had at takeoff. And there are a few techniques that you can use to do that, to be able to lean continually throughout the climb. First of all, your manufacturer may have a fuel flow schedule. Again, this is the Comanche, and it's marked directly on the fuel flow gauge here. We have markings for takeoff fuel flow, which is really just full power fuel flow, all the way from sea level up to 6,000 feet. And you can simply lean the mixture to match the fuel flow to whatever your altitude is as you climb. You don't have to do this continuously. You don't have to do it constantly and really stay on top of it. Every 1,000 feet or so is fine. Just tweak it back close to the line that's appropriate. And of course, verify that the CHTs are in a safe range. Because if they're too hot, then you probably need that extra cooling, that extra fuel for cooling. These sort of markings, if they're not directly on the fuel flow gauge, they may be in your POH, they may be on a placard in the panel. But if your manufacturer has done the work for you, test it out. This probably works just fine. If they haven't, if there isn't anything like this in your POH, you can create your own fuel flow schedule for a climb that's designed to maintain a constant fuel air ratio as you go up. And the way that you do that is by realizing that horsepower drops by about 3.3% per 1,000 feet. And with horsepower dropping off at that rate, fuel flow could drop off at that rate to maintain a constant fuel air ratio. And so all you do is you take your sea level fuel flow and you subtract 3.3% from it for each 1,000 feet, and you've got a nice fuel flow schedule. You want to start from a known good sea level fuel flow, and if you don't know what that should be, there are some rules of thumb for estimating what a full power fuel flow should be. If your engine is for engines up to 200 horsepower, 10% of the horsepower that you're making is a good estimate for fuel flow on takeoff. And so if you had 180 horsepower O360, should be seeing about 18 gallons per hour when it's making 180 horsepower. Anything above 200 horsepower, the rule is to divide by 11. So it's a little bit less than that, but this 250 horsepower Comanche comes with a 25 gallon per hour marking on the fuel flow gauge for sea level fuel flow. And you can think of that as a minimum. You don't want to be below that. You want to make sure that you have sufficient fuel flow for adequate cooling. Another method is the target EGT method. So the way that this works is that shortly after takeoff, you note the EGT. Any EGT works. Even if you have a single probe EGT, that'll work for this method. But you note where it is. And then as you climb, actually, I'd also suggest normalizing the engine monitor. Normalize mode on your engine monitor, if you have it, levels all the EGT and CHT bars at their current values and also increases their sensitivity. And we're going to be looking for deviations from where they are when you normalize it, so that makes it all the more easier to do. But then as you climb, the fuel air ratio naturally gets richer and EGT drops as a result, and you simply lean the mixture to bring the EGT back to that target value. You don't have to, again, be really on top of this. Just every so often, say every 1,000 feet, make a little pull on the mixture, glance back to that EGT to make sure it's in the ballpark, verify that CHTs are good, and do that throughout the climb. And this is what that looks like. We pulled the mixture back a bit. EGT came back up to right around that 1285 target. And then there you go. Back to CHTs for a moment. The goal of this method is to get a little bit more efficiency out of the airplane, a little bit more performance while maintaining a mixture that's rich enough for cooling. And so to know if your mixture is rich enough for cooling, of course, CHT is your reference. And if you have a factory CHT gauge, its red line is probably way too hot to be practical. This is a Lycoming CHT gauge, and it's got a red line at 500 degrees. That's actual real-time damage levels of CHT. And so you want to establish a more practical personal operating limitation here. If you have a Lycoming engine, a good personal red line is 420 degrees, and a personal yellow arc could begin at 400 degrees. So take some action when it gets above 400 degrees in order to keep it below 420. If you have a Continental engine, you can reduce those temperatures by about 20 degrees. So 380 is where a yellow arc starts. 400 is where you should consider your red line. Now, some aircraft run hotter than others. And, it's not like if you get to 421 degrees on a Lycoming, you're going to do damage. But the more that you can keep this below these levels, the better. I fly pretty often 180 horsepower 172 based in Wisconsin, and it just runs hot. And so I'll often see after takeoff CHTs on the hottest cylinders around 430, even on a not especially hot Wisconsin day. And so in that case, CHT is a limiting factor. I'm certainly not going to lean the mixture with the CHT peaking at 430. And so my method in that case is to leave the mixture full rich, do everything else that I can to keep the temperature from getting too out of control. And then once the CHT drops below a reasonable level, then I'll start to lean with CHT as the limiting factor. The trade-off in doing that is performance. Like I could get a little more performance out of that engine if I could lean it a bit. Trade-off is economy, but temperature cooling, not abusing the engine is much more important at that stage. And the trade-off in performance just doesn't matter all that much to me in Wisconsin at low elevation in a plane that already has a bit of extra horsepower to begin with. So you're always thinking in terms of these compromises and trade-offs and what's most important and what is your goal in a phase of flight. What do you do if CHTs are too hot in the climb? Well, three basic things that you can do in the cockpit. You can go faster and increase the cooling airflow over the cylinders. You can enrich the mixture we already talked about, and you want to ensure cowl flaps, if you have them, are open. And then, of course, there's some things that you can do if you're consistently having high CHTs that involve your mechanic, like checking the baffling and ensuring that you have enough fuel flow. All right, we're going to wrap things up there. I'll remind you that we have the airplane engine operations course. All the slides from this from the video course. Sorry, all the slides in the webinar were from the video course, and it's about 2.5 hours worth of demonstrations of these things. You can see that chart that we used animate in real time to follow along with the demonstrations. The recording will be available tomorrow on the Pilot Workshops YouTube channel. So show your friends, watch it again if you like. And thanks everybody for coming. I hope you all have a great rest of the day.